All right, everyone. So in today's class, we continued what we did on Tuesday. Well, the first thing we did was look at the domain of a power series. But just to give you a sense of where we're coming from, on Tuesday, we started really digging into what are called power series, or as you can think of them as infinitely long polynomials. We did things like differentiate them, we did things like integrate them, treated them like functions. And then our next idea was, well, if we treated them like functions, well, we should know what x values we're allowed to actually evaluate them at. As in, you give me an x value, if I plug it into the function or the power series, we should get a finite unique y value in return. Or as in, you give me an x, I give you one finite y value. So that led us to this question of what is the domain of power series in general? We basically talked about and applied the idea to a couple examples. We saw the first thing we always do is apply ratio test. And then this leads to the actual domain that we think about. And for us in this type of problem, the ideas where this led us in terms of what is the domain, we saw that there's basically three different cases that the domain of a power series can fall into. There's case one, where only one point is actually in the domain. This is the point in which the power series is actually centered. So the point in which the power series is centered is always in the domain. The next example we did, we saw where the domain is all x values, from minus infinity to positive infinity. So if you give me any x value, I should be able to plug it into our power series, and that power series should give me a finite value in return. And the last example that we started was basically where we saw a specific interval works in the domain. So for example, if the domain of a power series was from -3 or less, or values of x greater than or equal to -3, but less than 7, choosing any of those x values, plugging into the power series would give us a finite sum or a finite value in return. So where we left off was kind of an example that involved case number 3 here. And I'm just going to recreate that whole example all in one spot, even though we really just today in class discussed the last part that we didn't quite get to on Tuesday's class. So the example that we looked at on Tuesday was finding the domain of the following power series. The power series given by the function from n equals 1 to infinity, n over 3 to the n plus 1 times x plus 2 all raised to the n. So again, just thinking about this, since this is x plus 2, we have that this power series is centered at x equals -2. Okay. So if we're interested in finding, again, the domain of these power series, the first thing that we do is apply the ratio test. And the ratio test helps us more or less chisel down from minus infinity to positive infinity what chunk of x values will actually work, rather than us blindly just trying out random x values here or there to figure out which ones work. Ratio test really helps us narrow it down. So as we apply ratio test, we take the limit as n goes to infinity of the next term in the series, the n plus first term, divided by the previous nth term in our series. So for us, when we look at this, we take, again, limit as n goes to infinity. Our previous term in the series is just the series function that we're given, n over 3 to the n plus 1 times x plus 2 quantity to the n. So we can just write that, n over 3 to the n plus 1 times x plus 2, that whole thing raised to the n. Now when we plug in the n plus first term, well, basically we go back to the original series function. Anywhere there's an n, we will replace it with an n plus 1 to look at the n plus 1 term. So if we go ahead and do that, we'll have n plus 1 all over 3 to the n plus 1 plus 1, or 3 to the n plus 2, times x plus 2 raised to the n plus 1. And again, what we're hoping to see from ratio test is that this limit is less than 1, because that's when ratio test converges. Okay, let's go through a little bit of this algebra now. Okay, so I'm just rewriting the limit. To do this algebra, I'm first just going to pull these x plus 2 to the n plus 1 and the x plus 2 to the n and put them over each other. And then I'm going to look at, well, I have in the denominator this fraction that I'm dividing by, so I'm just going to reciprocate and multiply that on. So first I'll take the term in the numerator. So we have times n plus 1 all over 3 to the n plus 2. Now I'll multiply on the reciprocal of that term from the denominator. So we have 3 to the n plus 1 all over n. And here's where we can start simplifying some of the terms. So for example, if we look into this x plus 2 to the n plus 1, we could write this as x plus 2 to the n all times x plus 2 to the first. And we can cancel out then a factor of x plus 2 to the n from the numerator and denominator. So I'll just write what we have as we find out new stuff. So we have this limit. What we're carrying with here is the x plus 2 to the first. Let's see what else we can cancel from that previous line. Well, we have that 3 to the n plus 2. We can write this as 3 to the n plus 1, since we see that n plus 1 power in the other term, times 3 to the first. And then we can cancel out those 3 to the n plus 1s. So now we have a factor of 1 over 3 coming from that 3 to the first in that denominator term there. And next we have n plus 1 all over n. And now there's not much we can actually do with that term because we can't really simplify it too much from here. We'll see what happens in the limit in a moment. Zoom out a little bit. All right, so next. The next thing I'm going to note is this x plus 2. This has no n's attached to it. This 1 over 3 has no n's attached to it. So we could actually pull it outside of that the limit all entirely. Since it does not have any n's, this limit won't affect that term. But we will need to carry with it the absolute values. So you have the absolute value of x plus 2 all over absolute value of 3 times the limit as n goes to infinity of the absolute value of n plus 1 all over n. And now this quantity n plus 1 all over n, it's never going to be negative, so we could get rid of those absolute values if we wanted, or we could keep them around now. But the thing to note about this limit, as n goes to infinity, this numerator, n plus 1, that numerator is going towards infinity, and this denominator is also going towards infinity as n goes to infinity in this limit. So this looks like infinity over infinity, so we get to do a L'Hopital's. So I'll just keep the terms out in front. Also, we can just write this as a 3, since the absolute value of positive 3 is just 3. And then doing the L'Hopital's for this limit, we have, well, the limit of the absolute value derivative of that numerator is just 1. Derivative of that denominator with respect to n is also just 1. So what this limit looks like in this case is, well, the limit as n goes to infinity of the number 1, this whole limit is just equal to 1. So what we're left with is this term, x plus 2 in absolute values all over 3 as the result of our ratio test. And now what's special about ratio test when we apply it to power series, we get to choose values of x to make this less than 1. So again, what we want to happen is we want this to be less than 1, since this is when ratio test converges. So what's, again, special about these types of power series is we get to choose x values to make this happen. So that's what's new about applying ratio test to power series. So the next step I'm going to do, we're really going to focus in on this inequality now, since we want x plus 2 in absolute values over 3 to be less than 1. So I'm just going to rewrite that down below, but I'm going to multiply both sides by that 3, so we have x plus 2 in absolute values is less than 3. Now the reason why I'm doing this is this 3 on the right-hand side, we call this the radius of convergence. And again, this plus 2 means we're centered at minus 2. So what this means in practice is if we're sitting at minus 2 in this case, we can stretch our arms out 3 units in each direction and grab x values that also give us a finite sum in return, or x values that we can plug into the series. So again, I'll just write this a couple ways. So again, because the radius of convergence is 3, we can reach out in 3 units in each direction and grab x values that we also know will lead to a convergent series. The thing we don't quite know yet, though, is we don't know if we include those points at the very edges. Kind of like if we're reaching out 3 units with our arms, we don't know if the points our fingertips touch at the very end, if we include those or not. Okay. Now, we could also think about this more algebraically, too. If we have x plus 2 is less than 3 in absolute value, we can look at this inequality 2 different ways. We can look at it sort of what's given, x plus 2 is less than 3. So we have x has to be less than 1 when we subtract 1 or 2 from both sides. Or we take what we're given, x plus 2, we flip the sign and multiply the right-hand side by a negative. So we have x plus 2 is greater than negative 3. So if we subtract 2 from both sides, we get x must be greater than minus 5. So in this regard, if we put both of these ideas together, what we find of points in our domain so far is we find points in the domain that work fall between minus 5 and 1. Again, we don't know what happens at those endpoints, though. So we still don't know what happens exactly at x equals 5 and what happens at x equals 1. That is sort of the idea that we had up above, where we said we are sitting at x equals minus 2. We stretch our arms out 3 units because that's the radius of convergence in this problem. And our fingertips just barely graze the edge of those intervals at x equals 1 and x equals minus 5. We don't know if we include those points yet. So far we know the domain looks like the one above. Okay. So what we need to test now is test the endpoints. And what I mean by this is we are going to literally take those endpoints, x equals 1, x equals minus 5, plug them into the original power series, and look to see if that resulting power series, those individual ones, converge or diverge. If they converge, we will include that endpoint. If it diverges, we won't include that endpoint. So I know yesterday in Tuesday's class, we ended with looking at the x equals 1 endpoint. So let's just quickly review what happened there. Taking x equals 1, we'll plug that in the original power series. So I'll just write the power series down below. And again, anywhere there is an x in the original power series, we're going to plug in x is 1. So just plugging in x equals 1 and doing a little bit of simplification here. We have n over 3n plus 1. Then we have 3 to the n. So we're going to be able to cancel out some factors of 3 to the n. We can write that 3 to the n plus 1 as 3 to the n times a 3 to the first, and see that the 3 to the n's will then cancel. So this power series then becomes a series from n equals 1 to infinity of n all over 3. And again, the big picture here is if this series converges, then we include x equals 1 as an endpoint, as in we would do less than or equal to 1 up here. All right, so looking at this series, we want to know whether it converges or diverges. The first thing I'm going to think about is, well, test for divergence. We take the limit as n goes to infinity of n all over 3. This limit is equal to infinity. What that tells us from the test for divergence, since this is not equal to 0, the series is divergent. What that means for us in this power series case is we don't include that endpoint. As in, don't include the endpoint, we don't use less than or equal to. Okay, so that happens to be the x equals 1 endpoint. We plugged it in, we saw that that resulting series diverged, so we don't include it in our domain. What about the other one? We have x is minus 5. So let's go ahead and plug this value in. So again, we go back to our original power series. Anywhere there's an x, we're going to replace that in a moment with a minus 5. So plugging in minus 5 into our power series, doing a little bit of algebraic simplification. We have this as n all over 3 to the n plus 1. And now we have minus 5 plus 2, which is minus 3. We're raising that to the n. All right, and let's take a look at what we can simplify here. Well, we have this minus 3 to the n. We could rewrite this as a minus 1 to the n times a 3 to the n by itself. Since inside of this minus 3 to the n, we can think of this as a minus 1 times a 3, that whole thing in parentheses raised to the n power. Okay. The next thing we can simplify is, well, we can simplify, or we can algebraically adjust the 3 to the n plus 1 and write that as 3 to the n times 3 to the first. And now we see we can cancel out those 3 to the n's. So the resulting series we have looks like the following. We have n equals 1 to infinity of minus 1 to the n times n all over 3. If we take a look at this series is an alternating series because that minus 1 to the n and all the other terms are strictly positive. So again, if we're wondering whether this series converges or diverges, because this is an alternating series, the first thing we could try is, well, alternating series test. And for alternating series test, we need two statements to be true. We need the limit, as n goes to infinity, of the positive bn terms. We need this limit to be 0. And the second thing we need is we need that the bn's are decreasing. So the next term in the series of the strictly positive stuff is less than the previous term. Okay. So we need to show that these two things are true. And if these two things are true, then by alternating series test, the alternating series converges. So let's try it out. So again, in this case, it's probably good to define what our bn's would be. So let's apply alternating series. The bn's in this case are the terms that are strictly positive. So this is the n over 3. So let's apply this to number 1 and see what happens. So first, let's roll with number 1 here in the alternating series and see whether this holds. So we take the limit as n goes to infinity of that positive stuff, which is n over 3. This limit is equal to infinity, which is, well, not equal to 0. So alternating series test is inconclusive. Since this limit is not equal to 0, again, alternating series test can't tell us whether a series diverges. It is just inconclusive, and we look at another test. So alternating series test in this case is inconclusive. However, when we look at this limit looks awfully familiar, almost like another test we have, but a little different because we'll include the negative terms as a part of it. So even though we can't use alternating series test on this, we could try good old test for divergence. So if we apply the test for divergence now on this specific series, we go back and, well, we include the entire series function for test for divergence, which means we include the minus 1 to the n. We have this n all over 3. And again, for tests for divergence, to pass this, we would need a limit of 0, and then we go on to other tests to think about convergence or divergence. Tests for divergence just weeds out some, but not all divergent series for us. So what happens here as n goes to infinity? Well, as n goes to infinity, that n is going to infinity, but that minus 1 to the n is giving us either a +1, -1, +1, -1 forever and ever. So what this will look like as n goes to infinity, plus infinity, minus infinity, plus infinity, minus infinity, plus infinity, minus infinity. That limit is never settling down towards one value. So this limit does not exist. And since the limit does not exist, the series diverges. And again, in this particular case, where this is coming from, we're plugging in a specific x value, one of the endpoints from our original domain, and seeing if when we plug in that endpoint into our power series, whether that series converges and we include that endpoint, or whether that series diverges and we don't include it. Because this series diverges in this case, we don't include this endpoint. What that means for us in practice is when we go back to the original domain we found earlier, this domain was from -5 all the way till x is less than 1. And we tested each endpoint to see if we include those endpoints. However, we do not include either of those endpoints in this particular problem. So the domain of this power series is just that x values greater than -5, but less than 1. The other type of thing we can mention in this case is we're looking at the domain, what x values we're allowed to plug into a power series, but this also goes by another name. We would call this the interval of convergence. Basically, what x values are we allowed to put into that power series, that infinite series, that result in a finite sum? In this case, for this particular power series, it's just these x values greater than -5 but less than 1. In other problems, however, you might include one or both of the endpoints. It's just in this particular example, we don't include either. So we really have to test the endpoints for each power series that fall into this case 3 of when we're trying to figure out their domain. Okay. So that's the end of part 1 for today's class. The next part that I discuss is basically going into power series representations, where the first one we look at is for the function 1 over 1 minus x. So check out that video in a few minutes.